Good morning to everyone. I am Dinbandhu. I am thankful for getting a chance to present my topic in a thermal and fluid engineering conference. And my topic is techno-economic performance of the large air conditioned classroom with energy recovery system. As we know that the energy consumption and production of electricity, which is associated with fossil fuel like coal, oil, and natural gas, cause emission of carbon dioxide and emission of greenhouse gases, which is a serious concern for not only for India but also for the global community. And in developed country, heating ventilation, application of heating ventilation and conditioning system consume more than 45% of total building energy consumption. If the building like a classroom or auditorium, which is really high occupied, so maintaining the quality of air, we have required to supply a large amount of ventilation. And the outdoor air is very hot and humid, which may cause high ventilation load of high latent load of ventilation. And research show that the providing of high ventilation to the hot and humid climate consume about more than 50% of air conditioning energy just in cooling and humidification of outdoor air, and which will increase the which will increase the cooling load of the air conditioning system. So the generally we are going to talk in conventional air conditioning system when the outdoor air is passes from the cooling coil. It is required to cool below dew point temperature in order to get cool and dehumidify. And if the outdoor air is very humid, like latent load is very high, so can be required to overcool and further before supply to the conditioner, it's required to be reheat. So which further increase the cooling load of the air conditioning system. To avoid these challenges of and reduce the cooling load of the cooling coil, the energy recovery based cooling system may become a solution. And all the energy recovery bills, enthalpy bill is one of the best solution from because when in enthalpy bill there is interaction of sensible and latent load with the supply outdoor air and regeneration exhaust air. And the problem of overheating of air can be avoided with the application of and desiccant bill. During when air is passed from the desiccant bill, it has it has required to get dehumidify and heated and dehumidify. But the problem of application of these energy recovery bills like desiccant and enthalpy bill will increase the cost and also the make size system bulky. And also their increase of cost must be justified in terms of their saving energy potential. And, and based on literature review, there is some literature gap, and that based on that objective they decide like that these energy recovery wheel like enthalpy and desiccant wheel coated with the absorbent adsorbent and like silica gel. So when the high humid air is passes through these wheels, so there is interaction of moisture between the supply air and exhaust air. But after a time, these wheels get saturated. So we have required to regenerate. We are required further regenerate these wheels for their continuous operation. For regeneration of wheels, we have required some external source. Generally, all these studies show that they use either solar energy or for some based form of energy for uh, regeneration of these wheels. But use of low temperature room exhaust like which is at 26 degrees centigrade temperature is limited. And also very less studies available on the economic analysis of these energy recovery based these energy recovery like enthalpy in the condition system. And also there is almost no studies available for the degradation of enthalpy energy recovery wheel. Because when we are going to use this enthalpy wheel, so their performance is also going to degrade with time. And how the load is going to increase with degradation of time. So in our present study, to carry out the techno-economic analysis of air conditioning classroom building with enthalpy and desiccant wheel, and also the effect of performance degradation of enthalpy and desiccant wheel of system performance is also carried out. This is the the building considered for the present study is divided into blocks. Like this is the rectangular block and this is the circular block. and these blocks are further divided into cluster, and each block is divided into 4 cluster, 1, 2, 3, and 4 cluster. In present study, one cluster of rectangular block, which which is shown here. This is the cluster of rectangular block which contain 4 rooms, ground to 3rd floor, are selected for the present study. And this cluster is made with the help of Google SketchUp model, which is Transys plugin, which further model using a Transys component called Type 56 for calculation of building cooling load. And each cluster is cluster integrated with a dedicated outdoor air system and an air handling unit. The dedicated outdoor system consists of this enthalpy field and a cooling coil, and the air handling system further contain a cooling coil. Seating capacity of each classroom is considered 240 students, and the metabolic rate of each student considered here is 1.2 meet. Considered as 1.2 meet, with 1 meet is equal to 58.2 watt per meter square, and the average body area of the student considered as 1.7 watt, 1.7 meter square for the analysis. And the heat generated from the light and electrical equipment is considered as 15.6 watt and 1 kilowatt, which is associated with the projector in each classroom. And the class is scheduled from morning 8 a.m. to 1 p.m. with a lunch break from 1 to 2 p.m. again from 2 p.m. to 6 p.m. from Monday to Friday. There is no classes scheduled from the weekend like Saturday and Sunday. And the comfort condition side class is fixed at 26-degree drivable temperature and 50 degrees and 50-degree relative humidity for calculation of building load. This is the schematic diagram of energy recovery, centrally conditioned classroom based energy recovery. This is the rectangular cluster which is selected for the study. And outdoor air for ventilation passes through the enthalpy field, which is shown from point to 1 to 2. During the enthalpy field, there is the interaction on supply air, outdoor air, interact air, central and lateral load with the room exhaust air from process 10 to 11. After here, in enthalpy field, there is cooling and humidification of processes take place. After that, air further passes through the cooling coil 2, where it's further air supply air further goes cool and dehumidify. A centrally chiller plant, which is water cool chiller plant, is used for supply chilled water to the cooling coil 1 and cooling coil 2 for cooling and dehumidification of outdoor air. Again, at point 2, supply air passes through the desiccant wheel, where it exchange humidity with the room exhaust air, which is shown at 0.9 to 10 before mixing to the recirculated air. At point 4 and 5, it's further mixed with at point 4 air mixed with the classroom recirculated air, and after that it again passes through the cooling coil 2, where it's further cool and dehumidified before supplied to the conditioned classroom with the help of duct arrangement. And the condition of 7 is such that so that you can tackle the load can handle load of air conditioned classroom to maintain comfort condition. And this is Transys model, which is a model using Transys 17 for analysis of the building. And this enthalpy wheel, this is the desiccant wheel, and further this is the chiller, and this is model for type 56, which is used for which is the building selected classroom cluster of rectangular model. And this cycle, this is the air cycle, and this is chiller cycle, where the chilled water is passes from the cooling coil 1, then again it passes to the cooling coil 2, and it's sent back to the chiller. And this is the cooling water cycle, which is shown with cooling tower. And the load is centrally conditioned classroom consists two cooling coils. So load of the cooling coil is either in sensible and latent load is calculated. Sensible load difference in due to temperature, and latent load is the sum of difference due to the specific humidity, and total load is sum of the sensible and latent load. And the chiller capacity is calculated at the sum of both the cooling coil capacity. Percentage saving of cooling load is calculated with the cooling load with conventional system and the difference in cooling load with the application of energy recovery system. And the coefficient of performance is calculated in terms of their ideal COP. As the ideal COP of reverse Carnot, ideal COP is based on reverse Carnot cycle, which is a function of room temperature and uh, outdoor atmospheric temperature. As the outdoor atmospheric temperature continuously vary with time, so the ideal COP also changing with time. So for the sake of calculation of actual COP, for sake of simplicity, assume that the ratio of actual COP to the ideal COP is constant, and requiring power of operating system is calculated with the by dividing the hourly cooling coil capacity with the hourly variation of coefficient of performance. And for the economic analysis, life cycle cost is and payback period is calculated. The life cycle cost is the sum of initial cost and operating maintenance and repair cost, and RC the replacement cost, and this is salvage value. So it's salvage at the end of the system. All these costs is summed in terms of their present value, and present value is present value is calculated as in single present value discount factor or in uniform present value discount factor. Single present value factor is for one time investment, and uniform present value factor is used for the equal amount of investment with equivalent time into uniform amount of investment for equal interval of time. And payback period is calculated as the difference between the initial installation and supply installation cost, difference in supply installation of the conventional system with and without with energy recovery system, and divide with the operating and maintenance cost with conventional difference in sum of operating and maintenance cost with dedicated out system, and sum of operating maintenance cost with conventional system. This graph show the variation of building load with a month from February to November. In this analysis, the analysis carried out from the February to November because the cooling system is almost required for February to November for Kolkata climatic condition, which is located to India. And the graph show that the cooling building load is maximum for month of May and minimum for month of February, and there is also a considerable amount of latent load associated with the total cooling load. So here this graph show the variation of monthly cooling load with and without DOS system, and from February it's almost equal, for their saving is very less, and with March, April, May, the saving is going to increase, and the maximum saving is see from May, June, and July, and this saving is going to be more for some monsoon months, because this system is more effective for months when the outdoor air is high compared to November and February month. And as the system is this system is associated with two cooling coil 1 and coil 2, and the analysis of both the cooling coils shown in figure, that from February to November, and cooling coil 1 handle both. This is total cooling coil load and sensible cooling coil load of coil 1, and figure so that the cooling coil 1 handle both sensible and their latent load. But you are talking about cooling coil 2. The cooling coil 2 handle only maximum amount of sensible load with a little amount of latent load, and this so the effect of how the cooling load is going to increase with the depreciation or deterioration of the enthalpy bill effectiveness. And this is so here starting. This is when the newly installed bill the annual cooling capacity, and with the 100% degradation, this is cooling capacity. So with newly to 100% degradation of enthalpy bill effectiveness, the cooling load increase about 19%. So we have required to replace these enthalpy and desiccant wheel, so that we can maintain room in comfort level. This is the calculation of total cooling load and total energy consumption from February to November, and their saving in percentage saving with application of dedicated outdoor air system. And the result showed that with application dedicated outdoor air system, about 70% of saving in cooling load is possible. Uh, this is the result. This, this is the result. So with the calculation of life cycle cost with and without energy recovery system, and here the replacement cost of the water pump and chiller pump we consider for the 10 years. So we have required to replace two times for 25 life for 25 year of life span of uh, air conditioning chiller based air conditioning system, and the calculated life cycle cost value is 22.405 million with a discount rate of 8% is considered for this study. And life cycle cost calculated with energy recovery system, same discount factor. And one additional term is the replacement cost and installation supply maintenance of top energy recovery field system, and replacement cost of dedicated outdoor system, which consists desiccant and enthalpy bill is also added. So here the time of replacement type of dedicated outdoor air system is considered 15 years. So based on that, and all other things for same means the replacement of water pump and chiller is also 10 years. And the cost associated with the ducting and all other things is not considered in this study, because the difference between these two costs with conventional system and without energy system assumed to be same and assumed to be can be neglected. So the results show that the life cycle cost calculated with energy recovery system is less compared to conventional system. So this result show that the dedicated outdoor based air conditioning system is more vital alternative solution compared to conventional system. And this is the conclusion portion. The techno-economic ground is the technical economic front of large air conditioning system for classroom complex in Hotel Kolkata is carried out with using Transit 17 software, and with application of these and therapy and desiccant wheel can save out 70% of energy, and require cooling load with application of these with depreciation of degradation of enthalpy will is increased linearly, and with degradation from 0 to 100%, the required plant capacity will be increased from about 90%. And the calculated payback period means time required to recover the investment initial cost is about 6.7 years with constant enthalpy will effectiveness. And based on above conclusion, we can say that the dedicated outdoor air system with energy recovery system is more vital alternative in terms of economical as well as in the this is a bit more environment friendly. So these are the some references which is used in this study. Thank you for attention.